Okay, so in this video I'm going to talk about the heat equation. We are going to talk about the heat equation. Okay, so let's jump directly to the introduction for this and let's see what is the meaning of the heat equation. We are going to say that in the absence of sources or sinks within the medium, if we have any medium, okay, the one-dimensional partial differential equation modeling heat distribution, so we are going to distribute heat, or we are going to model heat distribution, means that whenever that we have a bar, for example, okay, and we want to know how the heat is going to be distributed or going to flow from one end, for example, if it's hot end here and this is cool end, how it is going to flow and what is the distribution over this length of the bar over the time, if we have time for this, so how it will be distributed and how it will be changing over time. So this is the meaning of the heat equation. And why we are using partial differential equation here? Because simply, as you are going to, as I have explained here right now, that our function is going to be still, it is going to be, if we say this is u, the function of whatever the heat or temperature, for example, it is function in two things. Number one, it is x, which is the distance, okay, that we are talking about, at where exactly the point that we are talking about. So there is one variable here, which is, we call it like the x-axis, and there is another variable, which is the t, which is going, t here means that it is the time. Let's put it like this, for example. This is time, and then the vertical axis is going to be our temperature, uppercase T, which is, or we can say this is the main function here, u of x and t. Okay. So we are having two variables that is contributing to the function that we are interested in modeling, which is the heat distribution. Okay, so now we can think about this, as I have mentioned before, that we have a bar, and this bar, it is going in this direction with x-axis, okay, and we are putting a heating source here, bigger here and smaller here, and you are going to find underneath or above this source of heat, it is going to, we are going to have like higher temperature at this part of the bar. However, here we are going to have also some temperature, but it is lower comparative to this part, and in between there is some kind of gradient in between that is linking the two. The point is, we want to know this function, which is giving us or describing for us the temperature over the length of the bar, how it will be changing with time, so we have the time variable here. This is why we need to think about the bar as if that it is laid here on the x-axis, and there is a perpendicular axis, which is the time axis, and then the vertical axis is going to be the temperature, so that we can say that at one particular time, okay, let's see, at time equal to 0, the distribution was something like this. But after like 1 minute, for example, or 1 second, or whatever the period of time, this distribution not going to be the same. It is going to be, let's assume that we are talking about a point of time here, for example, okay, so it is going to be, maybe it is going to be something like this, right? So it is here at t equal to 0, here t equal to, let's assume, for example, 2 seconds. Okay, so we have another distribution here. Okay, so we are moving into this direction with the time variable. Well, so we found after derivation that is the time or the rate of change of temperature with time, which we can say that it is partial U partial T. This is the rate of change of the temperature. Rate because we are using T, lowercase t. It is changing with time. So our function is changing with time. We found that the temperature changing with time, which is the first derivative of it, okay, it is related to something to the bar, or the distance on the bar itself, the point on the bar that is being described. So we found that the heat, or the partial differential equation that modeling our heat distribution, is going to link between two main parts here with a constant called K, which is representing the medium. The first part is the rate of change of our temperature function with time, which is going to be in this direction of time. It is going to be related to the second derivative, partial square u partial x squared, of the x, okay, in this direction. So this is how it is going to be described. I'm going to give more elaboration on this in the next slide. Let's see how we are going to deal with this. So here, the horizontal axis, we have x-axis, where that we are putting the bar here. As you can see, this is the bar, where that it has different colors, okay. This part here, it is hot, so we are going to find that our, for example, our first distribution function is going to be this. For example, let's assume it is this one, okay. So this is how, or this is, yes, how the first distribution function at time t equal to 0 for the bar, and the vertical axis is giving us the temperature, right? And this perpendicular axis to x, it is giving us time. So we found that after t, for example, at t equal to 3, after 1, 2, 3, for example, here 1, 2, 3, found that our, look here to the yellow, this yellow line here, yellow curve, it starts to be different than the red curve that I am having here. So we found that the rate of change of this function in the time direction, the rate of change is this one here. Let's assume it like this, which is partial u partial t. I'm going to show it in the next slide. It will be better. Here, look here. So this is the rate of change with respect of time, okay. So we are going to describe it as follows: partial t, which is the temperature, partial t small, which is the time, and it is, as we said, our function is described by two variables, two independent variables, which is the x, the distance itself, and the time. So this is the first part. Here we found there is a relation between the rate of change of t, temperature, with respect to t, which is the time, and this rate of change is exactly, it's the slope of this curve here. Look here, this is the curve here, okay. We found that it is related to what? Related to the partial derivative of the function along x-axis. Look here to this function. Look to this function here. This function, it is being described, the slope at any point here, it is going to be exactly partial. Let's assume partial t, partial x. Remember, we are talking about an x direction. So this is the slope here. We call it also the rate. Rate of change, we can call it like this. Rate of change in the temperature with respect to x, which is the variable, independent variable x, the distance along the bar. We found that these two are going to be related together, but Here we are not going to find that this rate of change of temperature is going to be directly related to the rate of change of temperature with respect to x. We found that it is related to exactly the second derivative, So we found that we can equate them, and we are going to put here like a constant k. This k is depending on the medium that we are talking about. Okay, many things, the medium and the conductivity of the bar and so on and so forth, and it is going to be given always. Okay, so this is the point that I want you to understand, that the rate of change of the temperature at a certain point on x-axis, okay, is going to be related to the rate of change of temperature with respect to the distance on this bar, okay, but it is actually related with the second derivative, partial square t partial x squared. And remember that we are talking about partial. Okay, why? Because we are talking about as u as function of two independent variables. Okay, u of x of t, or like capital T if you like to put it here in this as if in this drawing, as it is in this drawing. Okay, so now we could understand now that there is a rate of change along time, and there is a rate of change as well along x, and both are going to be related together, Okay, so this is the important part that I want you to know about about the understanding of our equation. Okay, of our equation. So our equation, as I said, partial u partial t, we totally understood now. And there is another thing, which is partial squared u partial x squared, which is the second derivative of this function that you are seeing here. It is along x-axis, is going to be related to one another through one k. We call this k, it is constant depending on the medium. Remember, well, whenever you are thinking about the heat equation, you need to think about three different axes, which is one is the distance, another one time, and the third one, of course, our main function, which is the temperature. Okay, so if you could understand the three different levels, or this kind of 3D understanding of the heat equation, then you are going to find it easy for you to understand. The point that might be arise in our minds is, what is the meaning of the second derivative here, and what is the meaning of the first derivative of the function in along the x direction, right? And here, this is a simple understanding of what we are having here. The red line here, as you can see, this is what we call it the temperature profile. It was hot here, which is in this area. It was hot also here, and in between there is a kind of like gradual change of temperature. We call this as u of x. This is the function in terms of x. Of course, we are talking about the temperature, so this is the temperature profile along the bar. When we are going to take the first derivative of this red line, we are going to call this first derivative as the temperature gradient. So we're going to find that the slope of this one, the temperature gradient, means that like the flow of heat from one point to another, we can distribute, or we can describe it better by the first derivative, temperature gradient. We can say at this point where that the temperature gradient is 0, we can find that it is the maximum change. It is going to be horizontal. The slope here is going to be horizontal, right? And we can find also here this point is going to be like 0 slope. Okay, so the gradient here is 0 at this point. Okay, no gradient here. Okay, and this is what we call it partial u partial x, which is the blue line, or the temperature gradient. And this is the first derivative, as I said. And after that, the green one is going to be exactly the second derivative. And this is what we call it the temperature okay, second derivative. This is the temperature change, okay, where that the temperature is going to be changed, and you are going to like see that it is function of the temperature gradient. We are going to tell that at this point, okay, the slope of the slope is going to be 0, or we can say that the slope of the gradient is going to be 0. The slope of the gradient is going to be 0, like there is, as if there is no change at this point of in the bar, okay, in terms of temperature. In a similar fashion also we can say that at this point here, this is kind of the slope of the gradient is horizontal. This means that we have the second derivative to be 0. Temperature change is 0 here, right? In a similar fashion here, we're going to find this is 0, second derivative, because the temperature gradient here is horizontal, okay? So this is how we can tell what is the meaning of the first derivative, which is the temperature gradient, and the second derivative, which is telling us the temperature change, okay, how the temperature change. And this is, as we said, we are talking about the second derivative here along along x-axis. We are talking here about x, okay? So this is partial u partial t, which is not seen in this 2D. It is like perpendicular on this plane, okay? And what is the meaning of temperature gradient actually? It is like telling us something like the something called the heat flux or heat flow, if you want to like understand it like quickly. So if we have 2 points on this temperature gradient curve, the upper point here means that greater heat flux, and the lower point is going to give us lower heat flux or flow. You can like understand it now like this, okay? That's the meaning of the temperature gradient and the first derivative. Okay, now I think that this is enough for this video. In the next video I'm going to talk about something else related to the heat equation with different boundary condition. Okay, thank you, and see you in the next video.